Chapter 1, slides 26 to 38. Now that we know how to write out a molecule, we want to now understand a little bit more about the three-dimensional shapes and charges that accompany these very flat 2D representations. So to do so, we've got to dial back to looking at orbitals, and we'll work our way up so that we can understand the three-dimensional nature and formal charges that accompany different atoms in different bonding situations. So let's start with atomic orbitals. In the 1920s, quantum mechanics was established as a theory to explain the wave properties of electrons. We want to move away from our elementary school level understanding of an atom as a solar system and move more towards the quantum mechanical model of wave-particle duality, right? The electrons are not orbiting the sun of the nucleus. Really, they're in some probable space as defined by these quantum mechanic models. So the way that we're going to look at it is not through math, but mathematical drawing representations. So we're going to simplify it in a qualitative way. So the solution to wave functions for electrons provides us with visual pictures, and it's these pictures we're going to be working with. And understand, these are mathematical model representations. So within a shell, right, as what you guys think of the orbit, there are different types of orbitals that the electrons can reside in. The first one is called an s orbital. I always think about electrons as being in some sort of yard, right? They're fenced in. If you have kids and you let them out of the house, the probability of them being in the fenced-in backyard is pretty high. There might be zero chance that they are, say, hanging the laundry, right? If you let them do whatever, there's zero probability that they're over there hanging the laundry, but very high probability of them bouncing the ball near the basketball hoop or something else. So that's what these probability diagrams really are, these wave probability diagrams. In an s orbital, it's defining the playground. It's saying that there's this, the probability is in this area here where the electrons are going to reside. And s orbitals are shaped like balls, like spheres. Right? So you think of them three-dimensionally, and you're showing here an x, y, z axis to show that this is a three-dimensional image. As the shells get larger, if you start filling a 2 shell or a 3 shell as you go down the periodic table, those s orbitals get bigger and bigger and bigger, bigger backyards. The type of orbital is identified by the shape. So this is the shape of an s orbital all the time. An orbital is a region where there is a calculated 90% probability of finding an electron, and the remaining 10% probability tapers off as you move away from the nucleus. So if you have a 1s orbital for a molecule, and for an atom, and it also has a 2s, look at the middle diagram. You see the 2s drawn, and inside is the 1s. So electrons behave, as I mentioned, like waves and like particles. So how can they be both? Maybe the theory's not yet complete. The theory does match experimental data. It matches observations that we have, witnessed and collected data for. So it has predictive capability. And so it's good enough for us to make amazing assumptions or hypotheses based on these theories alone. So like a wave on a lake, an electron's wave function can be positive or negative. And I don't like to use the positive and negative because, again, remember, these are mathematical equations. So if your wave is above the lake, then it's a positive wave. If it's below the lake in a trough, then it's negative. And these are given positive and negative because wave functions are mathematical schemes. In what we're doing, when we're representing things, I actually don't like to use positive and negative because People confuse it with the charge of the atom, and it has nothing to do with the charge of an atom. It's just explaining the mathematical function. And so I like to use colors. And in this course, if ever I'm talking about the phase of a wave function, I'll actually color them differently, because to us, because we're not doing the math, it doesn't matter if you know that that phase is positive and that phase is negative, as long as you know that they are different phases. So that's why I like the blue and the red representation rather than the positive and the negative, which just starts looking like charges, and that's not what we're meaning. The node is at the lake level, and the node is the zero probability of where an electron is likely to be. That wave function I just showed you is what more of the mathematical wave construct looks like for a p orbital. Because they're generated mathematically, we see the positives and negatives, but I will show you a p orbital looking like this, with a red and a blue or a black and a white lobe. So these are called lobes to the orbital. And again, these are three-dimensional, and they're pictorial representations of the math. Notice that there's a node right between the phase change, and that is saying that if this is the playground, right? If you have a p orbital for an atom, this is the playground for the electrons that reside in that orbital. They could be in the top lobe, the bottom lobe. They can shift between the lobes. I mean, it could be anywhere. That's your playground. But there's zero probability at the center. Don't let that fool you in thinking that the electrons only reside on one lobe or another. Now, there are three types of p orbitals. Well, it's the same. The p orbital shape is the same, but understand that an atom that has p orbitals has 2 electrons in each orbital, and those p orbitals can reside in one of 3 planes. So you could draw a p orbital using the y-axis. You can reorient that orbital, same shape, but put it in the x trajectory. And then you can reorient it a third time and put that p orbital into the z trajectory. I'd like you to draw an arrow to point to the nodes in each of these 2 p orbitals. If you said here and here and here, you are correct. Those are the nodes. Now, when you are doing electron configurations and you're filling p orbitals, these are the 3 p orbitals that make up the 6 electrons that house the 6 electrons in the p block. And we'll talk about these as we go over electron configuration. But understand, remember, each orbital can only have 2 electrons. So if we're talking about one s orbital, like a single s orbital, you can put 2 electrons in there. A single p orbital, like py, has 2 electrons that can be housed in there. So there's a maximum, remember, an orbital can only house 2 electrons. So if you want to house 6 electrons, you'll need 3 orbitals. With this in mind, and the periodic table as our tool, remember, skip the transition metals, we can really put together some helpful electron configurations that, allow us to understand these orbitals a little bit clearer and will help us build our foundation towards molecular orbitals. So let's complete the following electron configurations with our periodic table in hand, which is, you'll never have to figure out an electron configuration without the added tool of a periodic table. So here we have our periodic table, and I'm asking you to do boron. Okay, so you identify boron. There it is. And what you do is you read from left to right, top to bottom. So we start at the hydrogen, right? So we're filling the electrons until we get the valence electrons all the way to boron. So we start in shell 1. These are the shells, the onion shells, right? We start in shell 1 and we read from left to right, from hydrogen to helium, until we get to boron. And we do it like a typewriter. We shift sides. So in the 1s, if you think about this block right here as the S block, and you think of this block as the P block, the transition metals are the D block. They're D orbitals. I'm not going to discuss D orbitals, okay? I'm interested in S orbitals and P orbitals. So when I'm talking about the electron configuration for boron, we start with the 1, right? 1, and we're in the S block, right? We've got 1s1, 1s2. Am I at boron yet? Nope. But I have filled the S block for boron. 1s1, 1s2. And I represent electrons as half arrows. And using our principles from Gen Chem, I do one spinning up and one spinning down. That's why this is how we do it. So an electron, this represents an electron, and the half arrow is just indicating spin. Okay, so I went from hydrogen to helium. Now I'm in shell 2. So you can see I'm now in 2. And I have to go through the S block to get to boron. So I'm going to fill the S, because you always fill S. S is lower in energy than P. So the shell number, the lower the shell number, typically the lower the energy. You fill tighter from the nucleus outward. So you always fill the lower energy shells first, right? That makes sense. S orbitals are filled before P because they're lower in energy. So you're always going to fill the lower in energy ones before the higher ones. It gets a little trickier when you get to d orbitals because the shell number is different, and d orbitals are higher in energy, but they also shift in shell number. So they tend to have a lower shell number. So, but we're not going to talk about Ds right now. All right, so I've gotten through the 2s block. As I move across to boron, I now hit the first of the P block, but I'm still in shell number 2, so it's 2P. Notice that there are 3 orbitals represented by these energy lines, and they are all in the same row. If energy is on the y-axis, you can see that all 3 p orbitals are the same energy. This is called degenerate. So you can circle these. These are the degenerate orbitals. Degenerate just means that they're the same energy. Notice that 1s was lower in energy than 2s, and 2s, s orbitals, are lower in energy than 2p orbitals. So the lower the shell number, the lower the energy. S is also lower in energy than p. Each one of these 3 orbitals represents a p orbital, but one of them represents the px, one of them is the py, and one of them is the pz. And we're just going to fill them. It doesn't matter. I could have written y, z, x. It doesn't really matter. Just that there's 3 types of p orbitals, and we're going to start filling them. You fill one at a time, so I'm only going to have to put in 1, because once I put in 1 electron, I hit boron, and I'm done. So at the end of the day, it's 1s2, 2s2, 2p1 is the electron configuration for boron. Let's do carbon together. Carbon is just 1 over. I'm going to go through the same process, right? I have to start up at the top, and I fill the first shell, and I have to go, I need both of those to begin. So 1s1, 1s2. Now I'm in shell 2. I have to go through the whole S block, so 2s1, 2s2. And now I hit the P block, still in shell number 2, just across the way. Now I'm in the 2p, 2p1. And then I go to carbon, 2p2. I fill, same spin, but I'm going to fill across the degenerate p orbitals before doubling them up. So this is what the carbon electron configuration looks like. 1s2, 2s2, 2p2. You guys can finish nitrogen and oxygen as practice. What are the rules that govern our placement of these electrons, as I've just shown you? Well, the first rule, and this is, again, going back to your Gen Chem roots, is that the lowest energy orbitals fill up first. This is a good premise to learn, and this is going to come in handy as a little background knowledge to help us understand a few things moving forward. According to the order, 1s is lower in energy, then 2s is lower in energy, then 2p, and you can see how it goes from there. This is also called the Aufbau principle, or the building up principle. The second rule to remember is that electrons act as if they were spinning around an axis. So in many of the same ways that we see the Earth spinning, the spin can be in two orientations. You can have it spinning in one direction or reversed the spin. That's why we use the arrows. I use half arrows instead of full arrows, but we draw them as spin up or spin down. And a maximum of 2 electrons can occupy one orbital, and they must be of opposite spin or orientation. This is the Pauli exclusion principle. So you guys remember all these, right, from Gen Chem, because these are covered, and these are important. We won't use the Pauli exclusion principle, or I won't allude to it as much, but the Aufbau principle of the order of lowest energy type orbitals will come in handy as we talk about a few other topics. The last rule, or Hund's rule, is if 2 or more empty orbitals of equal energy, right, degenerate energy, are available, 1 electron occupies each with spins parallel to each other until all orbitals are half full. So electrons tend to be unpaired to the maximum extent. You can think of that as a repulsion. Let's go back to the previous slide. This is what we saw Hund's rule in action when we were filling carbon. We did 1s2, 2s2, but as we were filling the degenerate p orbitals, we were doing parallel spins, right? And we would fill across each one. We'd put one in each before we started doubling up. That's what's meant by Hund's rule. So here I have some practice for you guys so that you can practice a little bit more drawing the electron configurations of the following atoms. And when I say electron configurations, let's do carbons again, but I'm going to write it in the way I'm expecting you to. Carbons is 1s2, 2s2, 2p2. That's what's meant by electron configuration. So you would write, for carbon, 1s2, 2s2, 2p2. How many valence electrons does carbon have? 4. I know this because on the periodic table, carbon is in the 4th group. But I also can see that represented by my electron configuration. The outermost shell is shell 2, and there's a total of 2, 4 electrons. So you have to consider, you can't just look, the biggest mistake is that students will look at just the last orbital. But remember, orbitals only have 2 electrons in it, right? A valence shell can have more than 2 electrons in it. So when we're talking about valence electrons, we're talking about all the electrons in the outermost shell. And the outermost shell is shell 2. So you have to add up all of the electrons in shell 2. Try phosphorus, nitrogen, and chlorine as a review. Okay, let's expand. We're now going to move from individual atoms, the atomic theory of orbitals, to molecules. I also want to have us understand a little bit about formal charges. So once we have the atoms and electrons in place to satisfy the octet rule, we have to now look at each atom to determine whether a formal charge should be assigned. Now, I've already hinted at the fact that if you guys are getting really good at bond trends, this formal charge identification will become easier and easier and easier. You won't even have to do any math, although you could. There is a formula to calculate it. The formal charge for an atom is equal to the number of valence electrons. Well, that's okay. We know how to calculate that. So you just take the valence electrons, you subtract the number of lone pair electrons you see, and you minus half the number of bonding electrons. So that's the formula you can use. Trust me when I say you will not use this formula past this chapter. So I've got the formal charge formula written up here at the top again, but let's work through how this is operational. Okay, the formal charge, if you want to use it, you see that I've got H3O plus. Why does it have a plus there? Well, you take the formal charge of oxygen to be the valence electrons, right, which is the group number, valence electrons, which is 6. You subtract the non-bonding electrons. Well, the only electrons that are non-bonding is this lone pair, so there's 2 there, right? So this is the lone pair. The 2 electrons of the lone pair. And then you subtract half of the shared electrons. Shared electrons, there's 2, 4, 6 electrons being shared. Half of that is 3. So half of 6 is 3. So 6, right, which is your valence electrons, minus 2, the lone pair, minus 3 equals 1. And it's a positive 1. So therefore the oxygen has a +1 charge. You could do the same for NO+. Which atom has the charge on it? Now this is the other part. This is the reason why I don't necessarily like condensed formula with charges, because the way that they always write the charge at the end of the condensed formula, and sometimes the charge is not associated with the atom it's closest to in a condensed formula. It happens to be the case here, but it's not always the case. So people get confused oftentimes with where the charge is located. Drawing out the Lewis dot structure for NO, you can see that nitrogen has 5 valence electrons minus the 2 lone pair, right? The 2 electrons that aren't bonding, minus those 2. And then there are 2, 4, 6 electrons in those bonds, so half of that is 3. So there is no formal charge on the nitrogen. However, if you recall, you should already have known there was no formal charge on the nitrogen. Why? Because nitrogen is in its normal bond state. Remember I said nitrogen is in that 5th group, so it has 5 valence electrons. So it normally likes 3 bonds and a lone pair. And nitrogen has 3 bonds and a lone pair. So it's perfectly comfortable and should not have a charge to it. Oxygen, on the other hand, is in group 6 and has 6 valence electrons. It should have, in a normal day, it should have 2 bonds and 2 lone pairs. Oxygen doesn't have 2 bonds. It has 3 bonds and a lone pair. So if you think about it, you could do the formal charge calculation, right? 6 minus the 2 that you see, minus half of the 6 shared electrons to give you a +1, or you can compare it to its normal bond trend state. Normally, it likes to share with 2 bonds, and it likes to have lone pairs of 2. So it likes to have 2 sets of lone pairs all to itself, right? It only wants to share 2 bonds. So if you think about oxygen being kind of greedy, it has to share 3. Oh my God, it has to give up electrons to share. It has to do more sharing. That means I have less for myself. Therefore, you see a +1. You see the positive. So if you can identify when atoms are outside of their bond trend, you can spot where there's going to be formal charges more quickly. And sometimes you can rationalize which direction that charge is going to go. If it normally has 2 lone pairs all to itself and it has fewer now, fewer electrons means a positive charge. So there's a qualitative way to look at this. I think you should come up with a set of training cards for yourself and expand on the retrieval cue called common bonding patterns. So I showed you the common bonding patterns for carbon, nitrogen, oxygen, hydrogen, and the halogens. I want you to expand that set so that you're used to these atoms outside of their normal bond trends, because we're going to see them outside of their normal bond trends as well. It's important to first start with what's normal, right? This is the what's normal. Boron tends to have 3 bonds and no lone pairs, thus it won't have a charge. When carbon has 4 bonds, it's happy. When nitrogen has 3 bonds and a lone pair, we're good. Oxygen, 2 bonds and 2 lone pairs, we see that every day in water, right? Halogens, 1 bond, 3 lone pairs. This is what I need you to feel like. That's comfortable. Yup, that looks good. This is what needs to look good to you. When you see that they're not in that look good way, now you're heightened to say, there's a charge there, or there's probably a charge there. And you can quantitatively figure that out using the formal charge formula, or you can rationalize it based on what you know about its neutral state. If carbon only has 3 bonds and no lone pairs, it's in need of more, right? It has only 6 electrons around it. So it's really devoid of electrons. So you're going to see it with a positive charge. When carbon has 3 bonds with a lone pair, it's meeting its octet, right? It has an octet, but it's not in its normal bond trend. It has more electron density on it than normal. It doesn't have to share a lone pair set, so it has a negative charge. So you can rationalize which way the charge goes based on whether it's sharing more or sharing less. Make cards for these. Get faster, but also trust that it'll feel like memorization right now, but we're going to be using this so darn much that the training wheels will fly away. And by chapters 2 or 3, you'll start recognizing when things are outside of their bond trend. Here's a little practice for you. Calculate the formal charge of nitrogen in the following molecules. So first, I'm going to say to myself, nitrogen. I look on the periodic table, which I should always have handy, and I know that it's in group 5. So I draw the valence electrons. I know that the normal bond trend is 3 bonds and a lone pair. Okay? Which, as drawn, have 3 bonds and a lone pair? That nitrogen has no charge on it. This molecule, if you look at every single atom, meets its normal bond trend. The whole molecule is neutral. Okay, so now let's look at the first one. It's got 4 bonds and no lone pairs. When you compare it to its normal bond trend of 3 bonds and a lone pair, that lone pair, nitrogen is kind of greedy. It likes to have its own lone pair that it can do whatever it wants with and doesn't have to share it. So it's sharing more. So that means it has less electron to it. That nitrogen should have a positive charge associated with it, therefore. How about C? 3 bonds and a lone pair is typical, but I only see 2 bonds and 2 lone pairs. 2 lone pairs, wow! I've got a lot more electron density than normal. Look, it still has an octet, but it's just not a typical octet that it's used to. It has more than it normally has. More electrons means negative charge. Notice that I was able to decipher the charges on these without having to use the formal charge equation. Why don't you try the next one on your own? All right, so now that we understand how to have atom representation, and we're now looking at molecular representation, and then once we fully understand molecular representation, because we're still working on molecular representation using orbitals, we're ultimately going to get to molecular dipole moment. Interestingly, this is an MCAT question that we pulled a few years back, asking about which of the following Lewis structures best represents carbon dioxide. Carbon dioxide is CO2. Just thinking about bond trends and charges, now atoms, if they can help it, they don't want to be charged. So given what you know about bond trends and the fact that atoms would prefer not to have a charge, they'd all like to be neutral, they all want to have octets and be neutral, which one do you think best represents carbon dioxide?